And now I would like to introduce our first speaker, which is going to be Francisco Andrés Delfín. I invite him to share his screen with us. And Francisco will be talking today about the evaluation of a multi-layer chromium nitride with diamond bicarbonate as top coating obtained by PVD. So, Francisco, if you're ready, we are ready. We're looking very much forward to listen to your talk.
Okay, thank you so much for the presentation. Can you see the screen? Is okay? Okay, just moving this to not disturb. So I am a PhD student from National University of Technology in Argentina, and here I'm presenting this job as part of my thesis, which is about these DLC coatings at all. I'm sharing this job also with my colleagues from the Surface Engineering Group, Dr. Eugenia Dalibón, and our director, Dr. Sonia Bru. Okay, this is our country. This is Argentina, where the flag is situated. Is the capital city, Buenos Aires, but we live 300 kilometers north along the Uruguay River, so it's near the border with Uruguay. And also our university has a lot of other campus around the country. But what we are going to talk about today is about a company located in the center of the country in the province of Córdoba, 750 kilometers northwest from Buenos Aires, because they are producing DLC coatings in Argentina for the first time. I know this might not be new for you, but it is for us, and it's really important. So this company is located in a place where there is a very big industrial pole, so they share service with a lot of other industries. So DLC coatings, as you might know, they have a really low friction coefficient, they have a good wear resistance, they are chemically inert, they have a really low interaction with other chemicals, low corrosion rate, and they can be doped with different materials to get different properties out of them, which make them really interesting for every kind of application. What are we going to do, or what we want to do with these DLC coatings is to deposit them over mild alloy steels for mechanical applications, because we want to reduce friction, to reduce energy consumption and gas emissions in different mechanical applications. So this is why for this job we use IEC 4140 samples, or 42 chromium molybdenum 4, or 1.7225 as you may know it. We did a thermal treatment with quenching in oil, then tempering at 550 degrees, so it's a really high tempering temperature. So it's a low hardness but really high toughness of the material, so we know we can withstand a lot of mechanical forces in it. Then we take a group of these samples, we grind everything to 1000 grit, it's not a polished substrate. We took a group of them and nitride them to 500 degrees for 20 hours, and then we coat all the samples with this chromium DLC made by PVD plasma gas magnetron sputtering. So we have two sets of samples. One set is with the nitriding before, and the other one is without nitriding. So the ones nitrided and coated, we call them duplex, and the other ones, they are only coated. We did some analysis with these samples, normal characterization, nano hardness, XRD, Raman. We scanned the surface. We also watched the cross-section with the focus ion beam. And then we did some topological testing with the samples using this pin on disc apparatus. It's homemade from our university. We put 10 and 12 Newton normal load with a sliding distance of 1000 meters using an alumina counterpart of 6 millimeters diameter. And well, of course, we analyze the wear tracks and friction coefficient and everything. And then we also, because we want this coating to be adhered to the substrate, so we did a variable low scratch test to see how good was the adhesion. So this is the equipment this company Coating Tech brought 2 years ago maybe. It's from a German company named Semicon. This is Semicon's C800, this is sputter. They do different kind of coatings because they coat mostly cutting tools, but they can also do this DLC coating. So the way this works easily is a target from the material we want to deposit into our substrate attached to a magnet. Then we have vacuum inside, some inert or reactive gas inside of a chamber. We apply the electric field, we create some plasma, and then we take some particles from the target and deposit them on the substrate. So, particularly in this case, for this DLC, we got an anchor layer of chromium nitride before the DLC coating. So we put our chromium target with nitrogen reactive gas, so we form this chromium nitride. Then we start putting acetylene inside the chamber, so we get a gradient of chromium compounds deposit over the chromium nitride. So we go from chromium nitride, chromium carbonitride, and then chromium carbide on top. And after that, we focus the power on the graphite target, and we deposit these coatings, this DLC coating, chromium dope DLC coating, or amorphous carbon, hydrogenated amorphous carbon on top of the chromium nitride chromium compounds. So this is the part we are interested in the tribological application, this soft DLC coating. So here we have cross-section obtained with focus ion beam. This is the substrate. Here you can see the chromium nitride layer and also the gradient in the chromium compounds to from chromium nitride, chromium carbonitride to chromium carbides. And on top, this black part is the chromium dope DLC coating. The overall thickness of this is around 4 or 5 micrometers. It depends on the spins of the carousel inside the PVD coating and the position of the sample inside, but it's pretty much 4 or 5 micrometers. And the DLC part of the coating, the top layer, is 1.4 or 1.5 micrometers thick. The mechanical properties with a young modulus around 140 gigapascal, as we can expect, and the hardness around 12 gigapascal or 1200 HV roughly. Here we have an analysis of the surface using the SEM with EDS. If we see some random part of the surface, we got with EDS we got the signals of the carbon, of course, the most, the chromium the least because it's the doping. But we also see this kind of defects, bubbles or drops or whatever you want to call them, around 5 to 10 micrometers in diameter. They are some precipitates of chromium compounds that are made during the process because apparently it's not as clean as it should be to be deposited also the DLC on top. But we haven't seen any problem regarding this, but they exist. So here we have more characterization. We did the XRD of the samples. Of course, you cannot see the DLC coating in the XRD because it's amorphous, but you can see the peaks of the iron here and also all the peaks of the chromium compounds, chromium carbide nitrides and carbon nitrides. The problem is they share pretty much all the peaks and you need to do further investigation to differentiate them. So we don't know exactly which one of them are there, but they are there. And also we did, to characterize the DLC itself, Raman spectra, the Raman spectroscopy. So we have here our spectra with the differentiation of the D and G bands. They are clearly up there with a ratio of 0.58. And using the slope of the fluorescence background, we estimate the hydrogen content in 26%. So according to Robertson, this should be in the range of the soft hydrogenated amorphous carbon, I'm sorry, the hard part of the hydrogenated amorphous carbon, because it's around 30% hydrogen, and with a hardness between 10 and 20, we have 12 gigapascals, so it's characterized as that. So moving on onto the wear test, we use the pin on this first with 10 Newton load. This is for you to get an idea of the uncoated sample. 0.65 around is the friction coefficient with this load. And we see with the coating, the friction coefficient is around 0.1. It's really low, really good effect on there. The coated sample is slightly higher, but they are pretty much in the error range between both of them. When we check the wear of these samples, of course, nitrided is a really high wear. The non-coated sample and non-treated sample at all is like twice nitriding in wear rate. And here we see the coated and duplex sample with a really low wear rate, so we need to do a little bit of zoom in to see a difference. And here you can see the duplex, I mean nitrided, and then with the coating, it is almost 3 times lower wear than the only coated sample. So with the nitriding, we improve a little bit on the wear. And here you can see the optical microscopy of this wear tracks. Of course, nitrided is like really wide. It has some grooves on it, but the coated samples are slightly thinner. They seem a little bit better, but the only coated sample has this stripe here in the middle, which we believe it is the DLC coating delaminated from the surface because of a problem with the addition, because we are applying here almost 1.4 gigapascal of pressure with these conditions we are testing. So we believe this sample couldn't withstand this force, this pressure, so it started to delaminate. So for checking this, we did the SEM analysis with an EDS mapping. Here you can see this the same groove, and we have presence of carbon, of course, in all of the track, but in the middle it is slightly less intense. The signal is lower. And we also see the chromium is also present all over around because of the doping, but in the middle the signal is stronger. So here we have also the nitrogen signal was stronger in this place. So here we have the chromium compounds that are below the DLC that are exposed, so we have a delamination. And we also saw in the inner part of the track, in this delamination zone, the signals of aluminum and oxygen. So here there is the alumina of the counterpart is starting to put some debris only in this the attachment area because of how this works. When you have the DLC coating and start sliding with any material, you get the transfer layer of the sp2 fraction of the DLC coating, I mean the graphite fraction. So if you form the transfer layer and the third body, so you have an dry lubrication system, solid lubrication system. But here, when we start losing the DLC because of the high Hertzian pressure, we start rubbing the ball against this chromium nitride or chromium carbide or chromium compounds. So it starts to wear exactly in this area, but not in the other areas around. So this is the problem with this poor adhesion of the coating. Here we see another test because we wanted to check what we were seeing. We increase a little bit the load, only to 2 newtons extra, so to 12 newton, because we have a limitation of the load we can put on the tester, but this was good enough because we appreciate a difference in the friction coefficient now between duplex and coated sample, with the coated sample with higher friction coefficient, also the duplex sample with a slightly higher friction coefficient. This also might be due to a different ambience conditions compared to the last one. So this trigger another test we are doing now with different relative humidities, and we see here that the coated sample has more wear than before, but the duplex sample is still the same. So yeah, we saw more delamination in the coated sample due to the increase to 1.5 gigapascal in the contact pressure. So more delamination, which affects also the friction coefficient. And here to prove the addition, we did the scratch test, variable load scratch test from 1 to 101 Newton. And we see the start of the crackings at 13 Newton in the only coated sample, at 27 Newton, a full delamination in the only coated sample. But for the duplex sample at 27 Newton, it's just the beginning of the first crackings, and 63 Newtons for the full delaminations. So this is because of the nitride layer. It helps to dissipate the load we have applied here. So to get an idea, we have our metal with 350 HV harness. We have our coating with 1200 HV, so this is a huge difference of harness. But with the nitride before, we had like 600, 700 HV. So, and there is a gradient of harness also because of the diffusion of the nitrogen inside the coating. So it was for the better, and it helped to improve the addition of the coating. So to summarize everything I said, we can see it is possible to deposit these DLC coatings using PVD system. This might not be really true because we also, this is not pure PVD. Someone might call it a hybrid system between PVD and CVD because the carbon precursor is not only the graphite target but also the acetylene. So there is a mixture of where the carbon comes from, also the hydrogen comes from the acetylene, so it's not pure PVD. But it can be done because it's a PVD system anyways. We proved we have excellent wear resistance for mechanical applications, a really low friction coefficient, which is really important for energy saving purpose. And but we have this problem with the only coated sample that presents high wear due to poor addition, and the nitride did help to improve that addition, which was for better in the wear resistance. So we can extend the span of the life of mechanical components using this kind of combination of treatment. And also, of course, now in Argentina, we can produce this kind of DLC coatings and reduce the cost for local industries. The problem is the industry still doesn't know that much about these coatings, so we need to help them to know them and to use them to reduce the energy consumption. So, as we say, muchas gracias a todos. Thank you very much. Danke Leute für hören. So, if you have any question, I will be pleased to answer.
Yeah, thank you very much for the very nice presentation and for the insights about the first DLC coating possibility in Argentina. I think it's exciting news. When you see in the chat, there are already two questions from the audience. The first question goes a little bit towards the wear track. The person asked, when showing the wear track, the coated sample seemed to show more coating defects than the duplex sample. Did you perform roughness measurements, and is there any difference?
Yeah, there is a slightly difference in the roughness of both surfaces. We have a problem with the sandblasting process they perform before the depositing of the DLC coatings. But we are trying to fix that to check if there is actually a difference, because we believe it doesn't really matter, but yeah, there is a difference in the roughness.
The second question asks, what is the exact difference between the chromium dope DLC and the ACH chromium? What do you think about the application of TAC instead of the other one?
Amorphous carbon hydrogenated chromium doped DLC is the same. ACHCr is the same as chromium doped DLC. It's another way to type it. And using TAC, it's harder. I believe TAC has a hardness around 60 gigapascal instead of the 12 gigapascal we see here. And this is because we are depositing this over soft steel. So for depositing a coating with 60 gigapascal, you need a harder substrate to deposit on, because for mechanical applications, it's not going to be good enough, the addition.
The third question is, how did you estimate the H content? I would have asked the same, I believe.
It's a paper from Ferrari, I think, from the years 2000, 2002, I don't remember really well. They say you can estimate the hydrogen content because when you took the Raman spectra, it's not like a flat line in the background, so you see like this slight slope. So you measure that slope, and with a formula that's present in the paper, you can see, you can estimate the hydrogen content. Of course, this is going to be better with XPS, I think, but it's a technique to use, and it's slightly approved. We use it quite a lot.
So, last question, maybe a short answer before we move on to the next talk. Will you also do some experience with TAC?
No, because I don't have access to deposit a TAC coating, but I will do pure PVD coatings in the future, so it's going to be like more graphite, so it's going to be even softer. Not with TAC, it's going to be the other way around, softer DLC coatings.
Excellent. I think with that we can close your talk. Thank you very much for your presentation. Thank you very much for sharing the news. Thank you for the discussion, and also to the audience to ask some questions. And with that.